Your Tesla knows you're going to a supercharger before you get there. It looked at your navigation, calculated the outside temperature, estimated how long the drive will take. In 30 minutes before you arrive, it starts heating your battery, warming it up to exactly the right temperature so that when you plug in, the pack accepts maximum power. The cheap electric car you rented on holiday doesn't do any of this. You arrive at the same charger with a cold battery, and the charging rate is cut in half because the car detects thermal risk. Same charger, same physics, completely different experience. Because of one system, today we open up thermal management, the invisible system that decides how long your battery lives, how fast you can charge, and how much range you actually get in winter. Over the last 5 weeks on WattInside, we've walked through the anatomy of the EV, the battery pack, the BMS, the inverter, and the motors. Today, the system that keeps every one of those components alive. Because heat is the number one enemy of every part of your EV, and cold is the number two. Let's start with why this matters so much. Chapter 1. Why lithium-ion hates temperature. Lithium-ion cells have an extraordinarily narrow happy zone. Somewhere between 15 and 35 degrees Celsius, they operate perfectly. Below that, chemistry slows down. Above that, chemistry accelerates. And when chemistry accelerates in a lithium-ion cell, bad things happen. At 0 degrees Celsius, a fully charged pack loses roughly 20% of its usable energy. The chemistry literally slows down. Ions move less freely. The cell can't deliver as much current. At -20, that penalty doubles. Fast charging becomes essentially impossible. The BMS will refuse to accept high current because forcing lithium ions into a cold anode causes them to plate on the surface as metallic lithium. That plated lithium never comes back into solution. Every cold charge permanently damages the cell. On the hot end, above 45 degrees Celsius, the cell starts degrading rapidly. Above 60, you enter thermal runaway territory. One cell heats up, triggers its neighbors, and the whole pack can catch fire. Between these two failure modes, the entire job of the thermal system is to keep every cell inside that narrow 20-degree window, regardless of whether it's -20 outside or 45 outside, regardless of whether you're crawling in traffic or fast charging at 200 kilowatts. This is significantly harder than it sounds. Chapter 2. Passive cooling, and why it killed the early Nissan Leaf. The simplest thermal management is no thermal management at all. The Nissan Leaf from 2011 to 2018 used passive air cooling. There was no coolant, no pump, no refrigerant, just aluminum plates connecting the cells to the outside of the pack casing, hoping ambient airflow would carry heat away. This worked in mild climates. It worked terribly in Phoenix, Arizona. Phoenix Leafs from that generation are famous for having lost 40 to 50% of their battery capacity within 5 years. The heat cooked them repeatedly, and there was no active system to prevent it. Nissan finally switched to liquid cooling in the second-generation Leaf, but the damage to the reputation was done. And every generation of Nissan Leaf still trades at significant discount compared to Teslas of similar age. Because everyone remembers, passive cooling saves money at manufacture. It costs the owner far more over the life of the car. Chapter 3. Liquid cooling, the industry standard. Almost every EV built today uses liquid cooling. Coolant flows through channels next to the cells, absorbing heat and transferring it to a radiator, or in modern designs, to a heat pump. The coolant itself is typically a glycol water mix, the same fluid that goes in a combustion engine radiator. Nothing exotic. What changed is the routing. In a Tesla structural pack, coolant tubes are integrated between rows of cells, contacting them along their entire length. Every cell gets direct thermal contact with the loop. This maximizes heat transfer. Older designs sometimes only had cooling plates at the bottom of the module. Cells at the top ran significantly hotter. That temperature gradient across the pack accelerated degradation of the top cells, while the bottom ones stayed fine. Over time, the pack becomes limited by whichever cell degrades fastest. Modern integrated cooling essentially eliminates this problem. Every cell sees the same temperature. Every cell ages at the same rate. This is one of the reasons Tesla packs age so predictably. The thermal management is that good. Chapter 4. Heat pumps. The physics upgrade. Traditional HVAC systems generate heat by running electricity through a resistor, like a giant toaster. Efficient at turning electricity into heat, but wasteful of that heat. Every joule you use for the cabin is a joule you're not using for range. Around 2020, EVs started adopting heat pumps. The Tesla Model Y was the first mass-market EV to make it standard. A heat pump doesn't generate heat. It moves it. The same technology in a household air conditioner running in reverse. You extract heat energy from the outside air or from waste heat in the motor and inverter, and you move it to wherever you need it. Battery, cabin, anywhere. The efficiency is dramatic. A resistive heater is 100% efficient. A heat pump is often 300 to 500% efficient. It moves 3 to 5 times more heat energy than the electrical energy you put in. This is why modern EVs suffer less range loss in winter than older ones. Not because the batteries got better, because the thermal system finally stopped wasting energy on cabin heating. Below -10 degrees Celsius, heat pumps start losing efficiency. The air outside doesn't have enough thermal energy to extract. This is why range still drops in extreme cold, but the drop is much smaller than it used to be. Chapter 5. The precondition. The killer feature nobody talks about. Here's the thing that most owners of premium EVs love, and most owners of cheaper EVs never experience. Preconditioning is when the car actively warms the battery before you need it. On the way to a supercharger, before a scheduled trip in the morning, before fast acceleration on the track. The BMS looks at the destination in navigation, calculates the expected battery temperature on arrival. If it's below optimal for the type of charging that will happen, it starts routing warm coolant through the pack. By the time you plug in, the cells are at exactly the right temperature. The result is dramatic. A cold Tesla arriving at a supercharger might charge at 50 kilowatts. The same Tesla, preconditioned, charges at 250 kilowatts, 5 times faster. This is a software feature, not a hardware feature. Cheap EVs have the same hardware. They just don't have the sophistication in software to do it. If you're shopping for a used EV, ask about preconditioning specifically. It's the single largest difference in charging experience between premium and budget EVs. Chapter 6. The Octovalve. Peak thermal engineering. Tesla makes one specific component that has become legendary in the EV engineering world. The Octovalve. Before the Octovalve, thermal management systems had a separate valve for every possible loop. Battery loop, motor loop, cabin loop, radiator loop, refrigerant loop, each with its own valve, its own pump, its own control. The Octovalve integrates all of them into a single rotary valve with 8 ports, 12 possible flow configurations, 1 motorized rotation to switch between them. This allows heat to be routed intelligently in real time. Waste heat from the motor can go directly to the battery for preconditioning, then rerouted to the cabin heater, then to the outside radiator when everything is warm enough. All from a single valve controlled by software. The mechanical elegance is extraordinary, and it's just one example of how deeply thermal management has been engineered in modern EVs. Traditional automakers are still catching up. Many current EVs from established manufacturers still have separate valves and pumps for each loop, wasting energy and space compared to what Tesla ships. Here's something I want to point out. We've spent 5 weeks talking about the exciting components: the battery, the motor, the inverter, the software. Thermal management is the boring one. It's the one nobody makes marketing videos about. It's the one that doesn't sell cars. but it's the one that decides whether the exciting components you paid for will last 10 years or 3. It's the one that determines whether your range in winter drops 15% or 40%. It's the one that lets your Tesla charge at 250 kilowatts while your friend's cheap EV crawls along at 70. Boring engineering is often the most important engineering. So to recap, lithium-ion batteries need to stay between 15 and 35 degrees Celsius to be happy. Everything the thermal system does exist to keep them there. Passive cooling saves manufacturing cost and destroys battery life. Nissan Leafs from that era are the cautionary tale. Liquid cooling is now standard, but integration matters. Cells that all see the same temperature age at the same rate. Heat pumps have transformed winter EV efficiency by moving heat instead of generating it. Preconditioning is why premium EVs charge dramatically faster than budget ones. Same hardware, better software, and Tesla's Octovalve is peak thermal engineering, consolidating what used to require a dozen components into a single elegant valve. Next week, we go into something completely different: regenerative braking. Why your EV barely uses its brake pads. How the inverter turns the motor into a generator when you lift off the accelerator. And why one-pedal driving changes the entire feel of an electric car. If you found this useful, subscribe. Drop a comment with what surprised you most about EV thermal management. I read all of them.